got her PhD in 2011 from the University of Rome. Her PhD advisor was Alessandro Melchiori. She then went to a postdoc at the Institut d'Astrophysique, and then comes the best part of her career. She was a fellow here at the KICP, but then she was called back to the Institut d'Astrophysique in Paris, and most of her career has been spent working on Planck, creating the software that gets the scientific results out. And so she's going to tell us about the final results. And I should also say that we have this workshop over the next 2 days, Thursday and Friday, talking about the controversy about H-naught. Now, not everyone, I mean, Silvia and her colleagues don't think there's a controversy. They measured H-naught, and Wendy Friedman and Barry Medor, who are not here yet, don't think there's a controversy. And Skolnick does not think there's a controversy because they measured H-naught. And but the two results don't agree, and they could actually both be right, and it's very exciting. And so on our website is the schedule for that meeting, and so you may wish to come to that meeting. But before you go to that meeting, we're going to hear about the final results from Silvia.
Thanks. So hello everybody, it's a great pleasure to be here. It's the first time I come back to Chicago since I was a fellow here. I adored my time here and I'm so happy to be back. And I must confess, back in the days when I was living in Chicago, I was like, I really hope they're going to invite me to give the final Planck talk. I swear to God, I remember thinking this 3 years ago. And then Mike invited me to give this talk and I was so happy. So here it is. Today I'm going to mainly talk about the results on cosmological parameters, which is one of the many papers that we already submitted in July. Not the full Planck release is not completed yet. We are still working on some fundamental papers. One of those is the likelihood paper. And so also the likelihood codes that will allow people to check our results and play with the data. These codes are not available yet, but they will be very, very soon. And this talk will be, I hope, general enough that also people that are not in CMD can understand it. Then I think we will discuss more the systematics and more details at the workshop that Michael mentioned. So first of all, I want to acknowledge the fact that I'm here talking on behalf of the Planck collaboration, which is the very big collaboration with many, many brilliant people that contributed to this mission. You have in the room Eric Klingon and François Boucher, who were two of the fundamental pieces of this adventure, fundamental characters of this adventure. And I will start the talk just by giving you the classical 2 slides on CMB for those of you that are less familiar with the CMB. Just to remind you that we want to observe this radiation coming from the last scattering surface at a redshift of around 1100. This comes, say, at the epoch of recombination of the universe. And what's so special about this epoch is that before then the universe was completely ionized. Electrons and photons were strictly coupled through Thomson scattering. So essentially photons were not allowed to propagate freely for large distances. When protons and electrons recombine in neutral hydrogen, photons are finally free to propagate. So already these photons encode a lot of information about the initial condition of the universe, inflation, but also all the beautiful physics of the photobarometric fluid before recombination. Furthermore, these photons also interact again with the ionized electrons from the epoch of reionization of the universe, where first start to ionize the medium. And also they get distorted by weak gravitational lensing from the large-scale structure of the universe. So you can see that the CMB photons encode a lot of information, starting from the very early universe and through the whole history of the universe. So we observe these maps that are the maps of the temperature anisotropies of the CMB, but also what's special about these perturbations is that they are nearly Gaussian. And so essentially we can characterize the distribution of these perturbations just by, so what we usually do is to decompose these in spherical harmonics and essentially calculate the variance of the coefficients of this decomposition. This is just because since these perturbations are distributed as a Gaussian random field, all the meaningful information about cosmology is encoded in the two-point function, showing in the variance. And so the power spectra that you see all the time when we talk about the CMB are just these CLs, and we usually multiply these by a factor L plus 1 for different reasons. But essentially, this is just the variance of these conditions. And the interesting thing about this power spectra is that different L regions are affected by different physical phenomena that depend on cosmological parameters. And so by measuring these power spectra, we can infer a lot of information about, for example, the amount of dark matter, dark energy variance, and so on and so forth. The cool thing about the CMB is that we can also observe polarization anisotropies. And this is just due to the fact that Thomson scattering between photons and electrons in the presence of equadipole anisotropy produce linear polarization. And in the early universe, we know that there are sources of quadrupole anisotropies. One are scalar perturbations, so density perturbations, the same that mainly source the temperature anisotropies, and these produce the so-called D-modes, so this kind of pattern in the sky. But we can also have tensor perturbations, such as the ones given by primordial gravitational waves, which source both E-modes and D-modes, which is this kind of pattern here. And so here, this plot shows the power spectrum in temperature, in the E-modes, and here I want you to notice this bump here at large scales. This is a very peculiar feature from the reionization epoch. And this is the reason why a lot of CMB experiments focus on measuring E-modes at large scales, because this gives us information about the reionization epoch of the universe, and therefore the optical depth of reionization. And then this plot also shows the B-modes that we have not measured. This is from primordial gravitational waves. But what we have measured is B-modes from lensing. So essentially due to the fact that the weak lensing from the large-scale structure of the universe distorts the polarization pattern, producing a leakage between E-modes into B-modes. And the Planck satellite was designed to observe the CMB anisotropies. Primarily, the primary goal of Planck was to provide the ultimate measurement of the temperature anisotropies. But as I will show you later in the design of the satellite, it was decided also to put some polarized detectors that allowed us to measure the polarization as well. And so at the beginning, this was not conceived to be an experiment that would measure polarization, but indeed, so it was not designed to minimize, for example, systematics in polarization, but it did, in any case, a fantastic job in polarization as well. We've learned a lot from this, and I will show you some of these results. So Planck was the third generation full sky satellite after Probe and WMAP launched in 2009, operated until 2013. And it had 2 instruments on board for a total of 9 frequencies, the low frequency one between 30 and 70 gigahertz, and HFI, the high frequency one, between 100 and 857, with 7 of these channels between 30 and 353 gigahertz being sensitive to polarization. The reason why you want so many frequencies is that one of the challenges for CND experiments is to disentangle the emission of the CMB, which is a black body at a temperature of 2.7 Kelvin, from the emission of other astrophysical sources, for example, the galaxy, that contaminates the signal. So the fact of having so many channels allows us to do component separation and to disentangle these the different directions. We had 3 data releases, data and cosmology releases. The first one was in 2013, based on nominal emission. So essentially providing what ESA asked Planck to do. So to observe the sky for about 1 year. And at the time we based our results and we published the data only for temperature. This was because polarization was not ready to be used. And at large scales to constrain the optical depth to realization, we used WMAP data. Then a couple of years later, in 2015, we had our second data release, the full mission data, so about double the data for HFI, about 29 months, and 48 months for LFI, that lasted longer. And for our baseline was still, for cosmology was still based on temperature, but for the first time we showed the impact of using polarization from Planck, both at high L, so small scales, but also at large scales using essentially polarization from, as measured from LFI, which is the less constraining instrument on board. HFI is much more constraining, but in 2015, the HFI data were still not ready to go for polarization at large scales due to systematics. And so then we spent 3 years, this is to have our third and last release. This is still based on essentially the same data we had in 2015, full mission, but we worked a lot on improving our understanding of systematics in polarization. And at large scales, finally, the data from HFI is good enough to understand the systematics well enough to be measured, to be used for cosmology, in particular, to measure the optical depth to realization.
May I ask a question?
Sure.
So when and why do you stop operation? What defines the 4 year? There is no advantage.
For HFI is the cooling, so it's the helium-3. So when the helium-3 ran out, then that was it. For LFI, I think there was an extension which was at the beginning of the mission was not anticipated, but at some point you don't gain a lot of statistical.
Not even for polarization.
What's that?
Not even for polarization.
I mean, I guess, I'm not sure if it was technically possible, but I guess for sure for one was better, but for LFI, I guess, yeah, you wouldn't have gained much by pushing this.
Diminishing return versus cost.
Yeah.
Yeah? Very possible.
No, heavy operation, the satellite is a little key to operate the thing.
So what happened with example.
How many volumes?
Okay, good.
Okay. So I think there are three important things that one has to keep in mind to really understand this last legacy release. As I told you, we spent 3 years essentially on the same data we had in 2015. And this is not something that you see a lot in a lot of experiments. We don't have essentially, like much more statistical power this year. We really wanted to be sure to leave to the community something that could be used, like a legacy that could be as robust, that would be as robust as we could. So the focus of this year release was really, as I said, understanding and correcting the systematics, both at large scales and small scales in particular in polarization. And we believe that we corrected or understood the systematics well enough that the baseline for the legacy release can be polarization, temperature and polarization together, plus the information that we have from CND lensing, and I'm going to talk about this a little bit more later in the talk. The second important point, I think, is that whatever we've done on the data, so from 2013 to 2015, we doubled the data for HFI, and then we understood a lot of different systematics on the way, but no one of our scientific conclusions broadly changed. Details changed, but the main conclusions were really stable across the years. And the third point is that I feel that as a collaboration, we've always been extremely clear about what were our limitations and the things that we were not understanding. In 2015, we had 100 pages paper on the likelihood, on the tests, and the things that we were not understanding. 100 pages. I can tell you it was not fun. And people complain it's too long, and I'm like, yes, that's a dictionary. You have a doubt about, I don't know, this little piece of the pipeline. Just go there, you look for it, and you can see what we learned about that particular piece. And more than ever, we're going to try to do this again. We have still some remaining uncertainty in the treatment of systematics, and we tried to quantify this by having an alternative pipeline for the likelihoods to understand how much different choices can impact the final results. We still have some internal inconsistencies at the level of a couple of sigma in the data that someone very, very smart in the collaboration named curiosities. This is the problem was what do we call something that's 2 sigma-ish? So it's a statistical fluctuation, probably, but as a collaboration, we worry a lot about these 2 sigma things. It's not tension, what is it? It's a curiosity. So I'm going to talk about one of our curiosities in the talk to give you a feeling. And while we are in very good agreement with a lot of different external data sets, such as BAL, we still have mild to strong differences or tensions with some other, and notably with measurement on H0. And maybe this is something extremely interesting for the future, and we have now 2 days to discuss about this. So before really going into the cosmological results, I just wanted to give you a feeling of what these systematics are. I know that people say systematics, so people that are not in the field are it's a mysterious word of what that means in practice. So I think I will give you like a really general view of this, just because this is important for any CNV experiment that will measure the CNV in the next years. So one problem with in particular measurement of the polarized signal, is leakage. So polarized detectors for us measure a combination of intensity and the polarization, the Q and U Stokes parameters. And in order to disentangle intensity and polarization, what you have to do is essentially simply, for example, take the difference between two detectors observing the same pixel in the sky that observe the same pixel in the sky with two different angles, polarization angles. Or you can have also the same detector that observes the same pixel in the sky with two different orientations. And you subtract the one from the other, and you can then disentangle these different components. However, if you have any imperfection in, or any difference in the detectors, say you have a difference in the calibration of the two detectors or asymmetries in the beams, this can end up in mixing intensity and polarization. So basically, you will have some of these intensity signal that will leak into the polarization. And the problem is for the CMB that since temperature at the power spectrum level is 100 times larger than the polarization, any small imperfection of your detectors will end up giving you this kind of leakage. So this is in 2 words. This is like 3 years of work trying to get rid of this thing. The second thing is polarization efficiencies that were like a problem for us. So this is just your detectors, your polarized detectors are sensitive to polarized radiation at some level. Say you throw polarized radiation to your detector, it will absorb, say, 90% of it. And you characterize this in the lab. Funny thing, you then launch the satellite, you start measuring, and you discover that the uncertainties that were measured on the ground are probably underestimated by a factor of 5 to 10. By a factor of 5 to 10. So this was a big problem for us. So in some ways, polarization efficiencies had an error which was much larger than what we thought. And this is other like 6 months of work to actually be convinced that this is the problem and figure out how you correct for this. So this was just an example of the things that we've been playing with in these fun 3 years. So the result of all this work is the angular power spectra here in temperature. This is the cross correlation between temperature and polarization, and this is the E-mode power spectrum. For temperature, Planck delivered what it promised, ultimate measurement, which means sample variance limited or cosmic variance limited, measurement of the temperature until L of around 1600, which means essentially that the error bars that you see here until here, you cannot see the error bars here because they are super small. These are dominated by just the sample variance of the realization of our universe, not by instrumental errors. For polarization, this is not true, and clearly there will be a lot of possibility of improvement with the future experiments that are planned for the next years. But for now, these are essentially the most powerful polarization power spectra for cosmology that are available. This was, I think, this was a huge step for the field. All right. And the other piece that I want to add is CMB lensing that we also use for cosmology. So I already told you that CMB lensing can mix or make leak E modes into B modes. But for what's, say, as this talk is concerned, there are other 2 effects that are important and, say, even more interesting. So the first one is that the gravitational lensing modifies the angular power spectra at small scales. It smooths the peaks and the troughs of the angular power spectra, both in temperature and in polarization. And you can then understand this just because the lensing will, say, magnify and demagnify locally the angular power spectra. And then when you average all over the sky, essentially you smooth effectively the peaks, because in each of the regions of the sky where lensing is coherent, essentially this will change a little bit the angular scales at where the peaks we measured this effect at a level of 15 sigma. However, this is one of the curiosity I will come back later. So just remember this effect. CMB lensing smooths the peaks and the troughs of the angular power spectrum. The second effect, which is even more interesting for measuring the lensing power spectrum, is that lensing breaks the anisotropy of CMB. It introduces a non-Gaussian signal at the level of the 4-point correlation function, and one can use this in order to reconstruct the lensing potential. And one of the news from this year is that we added a point at lowish shells that equal 8 in the lensing reconstruction power spectrum. And although it seems like a little improvement, this is actually very interesting because it allows to constrain some models, such as compensated AC curvature models. So it's 1 point, but it's actually useful for models that predict actually excess of lensing at low wells. And Planck detects this at the level of 40 sigma, and it's the so far the only experiments that have measured the lensing potential of the sky. Okay, so we use all of this beautiful information to constrain the lambda CDM model. So here I just remind you what are the cosmological parameters that goes into this model. We have two parameters to describe the initial conditions of the perturbations. The scalar amplitude of the primordial power spectrum, which just governs the overall amplitude of the spectra. The scalar spectral index that just governs the tilt. The angular scale of the sound horizon, which essentially governs the position of the peaks. The optical depth to realization, which has an impact on the overall amplitude of the peaks, and as I showed you in polarization, it gives you a signal at large scales, a bump at large scales. And then two parameters for the energy content of the universe, in particular baryons, many different effects, but one of them is to change the relative amplitude of the first and second peak, and the physical density of dark matter that essentially changes the relative amplitude of the first and the third peaks. And then some other assumptions, such as 3 standard neutrinos, adiabatic initial conditions, 1 massive neutrino with a minimal mass at 0.06, and some very simple model for reionization. And for this simple model, actually, these are the results. I clearly don't want you to really look into this table with a lot of really into the details of this table. This is the mean, the uncertainty, the relative uncertainty for the 6 lambda CDM parameters I just described, and some derived parameters such as the Hubble constant or sigma h, which is the amplitude of the matter perturbations today. And there are a few interesting things in this table. So first of all, the fact that we really entered a phase where we measure cosmological parameters at the level of percent or even sub-percent, or in one case, sub-percent level. In this case is the case of the acoustic scale of sound horizon. We measure the parameter at the level of 0.03%. This is just due to the fact that this parameter, as I told you, tells you essentially the position of the peaks. And we now measure with Planck 7 peaks in temperature, 6 in TE, and 5 in EE. So it's a lot of data that tells you where these peaks are. And this, as a consequence, essentially you can have an extremely nice measurement of the acoustic, the angular scale of sound horizon. This is actually improved. So from temperature alone, you get 0.05, and then you go back down to 0.03 with polarization. The second thing that I want you to notice is the reionization optical depth. So for the ones, which is at 0.054 now. This corresponds to a reionization epoch that happened at around redshift 7. And this is relevant because for the ones of you that have followed, this value was much higher a few years ago from double map measurements that measured the reionization redshift to be around 10, which was very hard to explain in the reionization models. It required top 3 stars, and so on and so forth. And we think so, first with the LFI data in 2015 already, we saw that actually tau was lower than what measured by WMAP. And this year it's even further down. This is just because statistical fluctuations between LFI and HFI noise properties are different. But we think that the reason why WMAP had a high optical depth reionization was that the dust cleaning in WMAP was not as good as in Planck, just because Planck has this high frequency maps that allow us to better take into account the contamination from dust. And the other thing is that the error bar here has gone down to 13%. This is about twice, like a factor of 2 improvement compared to WMAP. Third thing to notice, I guess, is the scalar spectral index, which is now measured to be different from scaling variance at the level, it's more than 8 sigma accuracy. And this is important because this is a prediction of inflation. And this is true, actually, we check that even if you open up the lambda CDM model, you start to, put more parameters in. This remains true at the 3 sigma level. And finally, the Hubble constant. So for some people, this is low. For me, this is just the value of H naught. Measured to be 67.3 plus minus 0.5. This is the best indirect measurement of H naught today at the level of 0.8%. But you have to keep in mind that this is an indirect measurement. You have to assume lambda CDM in order to calculate H naught today. The CMB is not directly sensitive to this parameter. You have to have a model that tells you what happened in the universe between us and the CMB in order to calculate this value. This is the reason why this is the difference with direct determinations is interesting, as I will tell you in a minute. And just to mention that I told you that we have a second pipeline to measure these cosmological parameters, and for these parameters, the largest difference that we see between the 2 pipelines are smaller than half a sigma. So we think that these are robust, and in particular for H naught, we get exactly the same answer. Yes?
You remember what was the WMAP gain sigma?
For what?
For H sigma.
For what?
For H naught.
For H naught, it was more at the level of 2 kilometers per second per megaparsec. Yes, and I think the WMAP process video was 1.6. Around.
What's the difference between these 2 pipelines?
Very good question. So for temperature, we get exactly the same answers. We do very similar things, and apart some small details in how we treat the dust, we get exactly the same answer. The problem is polarization. So the polarization, I told you one of the things we worked on was how to correct for these polarization efficiencies of the detectors that we discovered that there are uncertainties that are larger than what we expected. And we have two different ways of measuring this, of having an estimate of how to correct this. And they, in particular, they differ for the cosmology analysis. We use 3 channels from HA5, 100, 143, and 217. And for the 143 gigahertz channel, we have a difference in what we estimate is the polar efficiency at the level of 3.5%. So one pipeline says there is no correction at 143 gigahertz. The other pipeline says there is a correction of 3.5% at the power spectrum level. And so this is one of the differences. This gives you differences of cosmological parameters that are at the level of half a sigma. And the second difference is that we use different masks. So the baseline pipeline uses 80%, 60%, and 50% of the sky at 100, 143, and 217. And the second pipeline, COMSPEC, uses only 50% of the sky. And the way we actually choose these regions, one is thresholded in intensity, the other one is thresholded in polarization. You do expect some variance just because we use different regions of the sky. We think that the differences that we get from the two masks is a little bit too large. So maybe there is also something going on with the differences in the masks. So these are the two main differences. Then there are details of how we treat the light mood and so on and so forth, but we actually check that all of the other differences do not count. It's really these two factors. Thank you. Very good question, and I'm sorry for the others that are not interested in this nitty-gritty details, but it's important.
So the values coded here are the average values?
Another excellent question. So we spent like one month discussing how we should present this data. So whether we should present the two results, whether we should present the results from one and then quote a systematic uncertainty, which was, I don't know, some difference between the results of the two. At the end, we decided these are just the numbers from the baseline pipeline, and then in the paper or whatever this makes a difference, we also quote the results from the second pipeline to give a sense to people how much, what's the level of robustness of the results. Again, no one of the scientific conclusions depend on these details, and the results can change at the level of half a sigma. And error bars in Planck are very short, so H naught cannot become 70 something, like just from this. And as I said, in particular, the Hubble constant we get from two pipelines is 67.3. I think I'm being extremely slow here. Oh wow, sorry. Yeah, I'm being extremely slow.
So let's take fewer questions.
Yeah, I guess it's better. Yeah.
I think it's been more the questions.
Yeah. So just one more word on the optical depth realization. So this is from HA5, as I told you, slightly different procedures at the first table. But anyway, any case, corresponds to a realization that happened at 7.6. We verified that this is in statistical agreement with what we get in 2015. And we also tried some the baseline model that we use for reionization is just something that, at some point there is reionization. It's modeled like a hyperbolic tangential, but you can actually open up the model and allow allow more freedom for the free electron fraction as a function of redshift. And we find that basically we don't find anything which differs from the baseline evolution, and in particular we don't find any evidence for substantial reionization at redshift higher than 15. Now the details of this number change a little bit with the priors that we put into the composition. Wayne has worked on this, and so these results can change a little bit depending on what exactly you do, but this is quite sound. I mean, whatever you change for the priors, this number changed by a small amount. This is quite a robust result. And so once we have these lambda CDM results, you want to compare with the external data sets, and we get very good consistency with baryon acoustic oscillation measurements, in particular the last BOSS results. Good agreement with redshift space distortions, good agreement with supernovae that Anton Pavlov led, and excellent agreement on the measurement of omega baryon here, but also omega baryon and the number of latinistic species as measured from primordial measurements of primordial deuterium and helium in combination with the Big Bang nucleosynthesis calculations. So here in gray, these are the measurements of the primordial elements. These are the predictions from the end. So the juncture between the two are the measurements of omega baryon from the primordial elements, and these agree extremely well within 1.5 sigma with the Planck measurements of omega baryon. I think this is, all of this is super cool. I mean, it means that our model and the physics that we understand works extremely well for a very large range of redshift. This is CNB and redshift 1100 agreeing with BBN calculations at redshift of 8. However, we have some mild differences with other cosmological probes. One, which has been with us since 2013, is with weak lensing surveys. So we started with CFHT lens, then KIDS came out, and then now we have the measurements from DES, and a few days ago, the Hyper Suprime camera from Subaru, the results of this survey came out, and they all give somewhat lower, here I show sigma 8, so the amplitude of the perturbations, the minor perturbation, and omega m, so this is Planck in blue, and you can see that, so these experiments basically measure a combination of sigma 8 and omega m, are a little bit lower at the 2 sigma-ish level compared to Planck. Actually, with DS lensing, we are fine. It's when we combine them with galaxy lensing and galaxy-galaxy clustering that also DS is a bit too low, at the level of a little bit more than a couple of sigma. What's happening here? I don't know. This is as I said, at the level of a couple of sigma, it's something that the community has to understand. So this is still there, and however, I think, while these can be still details, I think, that can be ironed out, this is the very interesting thing that we are all talking about, the strong tension between the Planck measurement and the direct measurements from supernovae and calibrated with the Cepheids, so with the distance ladder, the SHOES program that gives you 73.5 plus minus 1.6. Now, this has been with us since 2013. In 2013 was 2.5 sigma, now we are at a difference of 3.6 sigma. This is just because the two collaborations just decreased their error bars in the year. And at the beginning was really like, two groups, one against the other. You have the systematic, no, you have the systematic. And it was just, just blaming one another that, we haven't understood our data. Cool thing, in these years, we have, looked at the data a lot. So there have been a lot of reanalysis of this 2011 results. Same thing for Planck. We really try to understand, whether there is a problem here. So no one found a systematic that can really explain this difference. Plus, the very interesting thing that happened in the last years is that we have now other probes that are starting to measure H0 at the same level of accuracy than these two. One is the inverse distance ladder. So if you, that basically uses BAO that are sensitive to a combination of omega matter, H0, and omega baryon. So you want to measure, to break this degeneracy, and one way is to measure omega baryon using BBN plus primordial deuterium, as I showed you before. And adding something at high redshifts to break further the degeneracy between omega n and H0. And this can be CMB lensing, as we did in the Planck paper, but this was already done with the Lyman alpha BAOs that are redshift larger than 2, or even the DES lensing. This was done also for DES lensing. And in particular, with these two methods, this is completely independent of CMB measurements. And actually, in all these cases, you get H0, which is low, at the level of 67.9 plus minus 1.3. And the thing to keep in mind is that also this measurement is model dependent. Okay, you have to assume lambda CDM in order for this to work. So this is not a direct measurement. There are other measurements of H0 that are still not at the level of fuse, but are getting there. For example, time delay multiply imaged quasars, that they seem also to recover a high H0 with somewhat larger uncertainties. These are hard measurements to do. They require very good modeling of the lenses and so forth. But they are there, they are getting high H0. And soon we hope that gravitational waves will give us a measurement of H0. For the moment, uncertainties are very, very large, but Dan promises us that in 5 years, they will solve any of our. It will be done. Check. Done. So again, what's going on in here? I guess there are always three possibilities, right? One, it's a statistical fluctuation. 3.6 sigma starts to be a little bit too large with just a fluctuation. Second hypothesis, systematics. But then if you start having multiple measurements, then you have to explain systematics in multiple probes. Third, maybe it's physics. Maybe the lambda CDM model is failing. And if we extend the lambda CDM model for Planck and the BAOs in a clever ways, then we can reconcile the measurement of H0 with the one from supernovae and things. However, I will show you that this is not trivial. People have tried many different ways to solve for this. I will not talk a lot more about this because I don't have time, but this is also not a trivial thing to do. And I just want to mention, before just showing you a couple of extensions, just to give you the flavor of things, one of our curiosities that we don't completely understand. which is the peak smoothing in the angular power spectra. I told you that in the angular power spectra, one of the effects of weak gravitational lensing is to smooth the peaks and the troughs of temperature and polarization. And we can measure this by parameterizing this with this parameter A lens. This was just a cross-check at the beginning. We had this, we said, okay, we want to measure this effect in CMB. What we're going to do is just to introduce multiplicative amplitude to the lensing potential that then is used to lens the CMB, the theory CMB power spectra that then we compare to the data. In the lambda CDM model, this should be 1, and since 2013, this is 2 sigma high, 2 sigma-ish. This is from temperature, 2.4 sigma high. We know this is not lensing because we have the lensing reconstruction from the 4-point correlation function that tells us that there's nothing wrong with lensing. It's not high compared to the lambda CDM parameters or the predictions of lambda CDM. And the problem with this is that some other extensions of lambda CDM, such as curvature or W, which are the dark energy equation of state, that are weakly constrained by Planck directly, but that impact the amplitude of lensing, can have small deviations from lambda CDM from Planck alone because of this effect. And we know this is not physical because as soon as we throw in other probes, such as BAOs, they go back to lambda CDM with very small error bars. And the unfortunate thing is that for a long time we thought, well, for a long time, we actually had the hope that polarization could help in understanding what was going on at high L with this lensing problem. But the problem is that the lensing effect is somewhat degenerate with some of the systematics that we correct in polarization. So depending on what you do exactly, so these are the two pipelines, the baseline and the alternative likelihoods, you can have a deviation of this A lens parameter that can be go up to 2.8 sigma or be 2.1 sigma. So why do I tell you this? This is just to keep in mind that we have this curiosity. It's a 2 sigma-ish, and when we combine temperature and polarization, it depends a little bit on the treatment of systematics. So don't jump on your cysts. You see the thing that is 3 sigma-ish. Oh my God, maybe there is something there. No, maybe there is something that we don't understand completely in polarization. This could be just a 2 sigma-ish thing. And in temperature, this can still be like a statistical fluctuation. We looked at this a lot. It's something that we see across frequencies, which is one of the reasons why we say this is not evidently a systematic, because something across frequencies, it means something across detectors. So you have to have a systematic that behaves in the same way across many different detectors. This is not trivial to do. We tried rings. Eric will talk about how much we believe about this tomorrow at the workshop. So we tried many different things. We don't find evidence that this is a problem. But anyway, this is an entire talk. The only thing that I wanted to show you for extensions of lambda CDM is indeed the effect of this extra smoothing. So what I was telling you about, for example, for curvature from Planck alone, if you look at our results, you have these long tails. So this is omega k and omega m. There is a big degeneracy between the two. But you can see that this tail really extends to negative values of omega k. This is just because negative omega k gives you a little bit more lensing, and so the angular power spectra at high L are happier. But as soon as we put, this gives us a constraint on omega k at the level of 10 to the minus 1. We add lensing, 10 to the minus, the uncertainty goes down to 10 to the minus 2, and as soon as we throw in the BAOs, we have an uncertainty of 10 to the minus 3 and centered on lambda CDM. And something similar happens with the dark energy equation of state. Planck, you see that the constraints are very large. This is for W0, WA. Very large because CMD is not very sensitive itself to these parameters. As soon as we put things that are constrained, things much better, we are back well centered on lambda CDM. And I think the last thing that I want to say, since I think I ran out of time, is this one, the constraints that we get on the number of relativistic species. So you know that the CMD is sensitive to NF, which is a parameter that, say, it's a way of parameterizing either the fact that you can have light relativistic species in the early universe, apart from the 3 standard neutrinos, or it's also parameterized as non-standard thermal histories. And this was, so when we open up this parameter, we find something which is extremely consistent with the standard value that we have in the baseline. So 3 neutrinos. But this is important because it was one of the parameters that people were claiming that can solve the H0 tension. And this is because there is a degeneracy between the number of relativistic species and H0 in the CMD, simply due to the fact that H0 changes the distance to the last scattering surface. If you want to keep the angular scale of the sound horizon, essentially theta, fixed, which is something that we measure extremely well, then you have to change the physical dimension of the sound horizon, and you do this by changing the expansion history at last scattering by changing the radiation density, so NF. And however, you know, when we open this up, since this is in very good agreement with the standard value that we put when we run with lambda CDM, also H0 is just fixed at the value that, or you know, close to the value that we get from lambda CDM, exactly the same value. Just the error bar, due to this degeneracy, goes up by about a factor of 2. But the tension, you know, goes down from being 3.6 sigma to a 3.2 sigma. So a few years ago, when the data were less constraining and we were using temperature alone, you know, you could go down to a couple of sigma, and then, you know, you would say, okay, it's a statistical fluctuation, plus you have some relativistic species in the universe. But now this doesn't work anymore. I mean, our constraints are strong enough so that this model doesn't work. And we tried this with many other extensions of lambda CDM. No single extension can actually, for the moment, explain this difference and not break up some other, you know, cosmological measurement. Not only the CMD, you have to see, you know, the BAOs, the supernovae, and so on and so forth. And just to mention, we also measure neutrino masses. The constraint on the sum of the neutrino masses has gone down by a lot since 2015, from about 0.5 at 2 sigma to 0.3, 0.26. And this is essentially due to the fact that we measure the large scale polarization now much better with HFI. This decreased and tightened the constraint on the optical depth reionization. And there is this degeneracy between the optical depth reionization, the amplitude of the scalar perturbations, and so the sum of the neutrino masses in the lensing measurement, which actually gives us these numbers. And so by breaking this degeneracy, we were able to improve these by a lot this year. And if we combine with BAO further down, we go further down to 0.1 ED, which is very close to the ensemble inverted and normal hierarchy. This is a model-dependent, somewhat model-dependent measurement, but it starts to be very interesting. And well, since it's the last slide, you've been very patient. I will just finish the talk with this. Planck has been a fantastic machine to, probe the predictions from inflation so far. Things are working extremely well. These are the constraints for the tensor to scalar ratio as a function of the scalar spectral index NS. And from Planck, we get a constraint on this just by the fact that tensor perturbations contribute to the temperature anisotropies, especially at large scales. And from that, you get a constraint that is at the level of 0.1. But this is already a cosmic variance limited measurement. To do better, you have to really go and measure the p-modes. And this is what the KICP collaboration is doing. And so the blue contours is what happens when you combine Planck and KICP. And the interest of this plot that you see all the time when people talk about inflation is that from this you can actually set constraints on the shape of the inflaton potential. And these are just examples for if a single scalar field minimally coupled with potential which goes as a power of some power of n, and shows you that you can start ruling out these kind of models. Many different models have been excluded by these constraints. I'm not showing them here, but this is just to give you a sense of why these kind of plots are important. Planck has measured, in combination with other cosmological parameter, flat universe, NS different from 1, so nearly scaling variant, but not really. No running of the running with Gaussian adiabatic perturbations. So lambda CDM seems to be extremely quite healthy, not for the H0 tension. I think that it's the biggest possibility that lambda CDM is breaking, or sign that lambda CDM might be breaking. We don't know for the moment. And that inflation seems to be still very so thank you very much. Thanks for the patient for this.
Thank you so much, Silvia, for telling us about these beautiful Planck results and preparing us for our workshop. We have time for a few questions. Carlos.
So if you...
I said we had time for questions, not for comments. If you want to hand me an envelope with money in it, you could have a comment. But...
So when you vary, you put the limit on neutrino masses and the number of extra relative degrees of freedom. If you combine both, so let both vary at the same time, what happens? Nothing.
Nothing. There used to be like a little bit more degeneracy between the two. Now the data are so good that constraints are the same even when yeah, we do also more creative things. We tried, massive sterile neutrinos and so on.
Correct.
So we have a question from Brad Benson.
Yeah. So how much, especially some of these neutrino constraints, neutrino mass, NF, how much are they related or driven by some of these oddities? There's this high lens, there's this, a high L factor that's sort of pulling H0 down, that also wants the lower NF, How much are you worried those things are related to those issues?
For NF, I think things are pretty sound. I don't remember whether, so I say this because, so we have this difference in this A-lens parameter between the two pipelines. So I told you that we have like a 2.8 sigma deviation from 1 and 2.1 sigma deviation, so it's different with 0.5 sigma. So by running the two pipelines, we look at the differences between the two, and this gives you a little bit the sense of how much, different measurements of A-lens also project in differences in extensions of lambda CDM. For NF, we don't find any difference between the two pipelines, so this is robust against probably corrections of systematics in polarization. For the neutrino mass, we do see a difference, and it's at the level of 15%. So this is probably the uncertainty that we have there from systematics. Then, in general, I mean, both pipelines measure this deviation at a couple of sigma level. You cannot, due to this extra smoothing, and it's true that this will tighten the constraint on the neutrino mass. This was indeed the third extension that is affected by this curiosity. And this is just because since our angular power spectra prefer a higher value of, a higher amplitude of lensing, since the effect of neutrino masses is to smooth the lensing potential, actually the fact that you would like a negative neutrino mass to increase the lensing potential instead of a non-zero neutrino mass. So this will push a little bit the constraints to be low. I think, you know, then when you combine with PAOs, you break a lot of degeneracies. I am not sure how much this number, it's easy to check. Yeah, that's actually Tom asked me about this. I told you that I would check. But yeah.
Okay, let's thank Silvia again.